Hello there and welcome to a brand new lesson. This is How Beyond Numbers where we learn maths the easy way. In this lesson, you're looking at injective and then surjective functions. By the end of this lesson, you should be able to define injective function and test whether a function is injective or not. You should be able to define surjective functions and test whether a function is surjective or not. You should be able to define bijective functions as though that are both injective and surjective. You should be able to use the horizontal line test to determine injectivity from a graph. And finally, you should be able to classify given functions as either injective, surjective, bijective, or none of these. The following are some terms that we would be using as we proceed in this lesson. You can pause at this moment and then quickly take a glance. I'll be talking about some of them before we proceed as well. Without much ado, my request to you is that you take your notebooks and your pens so you practice along as we study. So let's start by explaining the three main terms we'll be working on. The first one being injective. I'll try my best and then give you some images or diagrams to enhance your understanding. So, say a function is injective, it simply means it is a one-to-one function. It being one-to-one function simply means that there are no 2 points in the domain that will give you the same element in the codomain. So every two parts do not land on the same spot, but rather each and every part lands on a particular target. You see, so every starting point has its own target. That is what we mean by injective. Then it simply means that if f of A is actually equal to f of B, the only way this can be possible if when A is actually equal to what? B. If a function satisfies this, then we say it is injective. Now for this diagram you see over here, the function is f of x equals x plus 10. So f of x equals what? An x plus 10. You realize that all the elements in here in the domain are mapped to exactly one element in the codomain. There is no element that maps to what? More than one. So with that, we can say it is injective. Every element in the domain maps to exactly one element in the codomain. On the other hand, there is what we call the surjective. The surjective's focus is rather on the codomain. So while the injective focus is on the domain, the surjective focus is on the codomain. So it says if every y in the codomain has at least one element in the domain, then it is surjective. You see, so what we simply mean is if we take our codomain, all the elements in the codomain should be pointing to an element in the domain. So it should mean that for f of x is equal to y, the solution always exists. Let's go to our diagram and then see what it simply means. If you look at what we have over here, we have an indication here that even says it is not surjective. The reason being that there are elements in this codomain that do not have what? They do not have corresponding elements in the domain. Hence, they are not surjective. So let's take another function and see. So for the surjective, let's take a function as f of x being equal to what? An x squared. So with this function, if I put x to be -1, -1 is going to give me what? A 1. If I put x to be 0, I'm also going to get what? A 1. If I put x to be 1, what do I get? I also get a 1. If I put x to be 2, I also get a 4. If I put x to be 3, I also get a 9. And you realize that every element in this set B we have over here is being traced toward an element in the domain. So it says every element in the codomain that exists in the domain with what f of x giving us the y. This is what we call surjective. You would realize that unlike the previous one, we said that is the injective, every element should map to one only, and they should all have a unique path. But if you look at -1 and 1, they don't have a unique path. They all point to 1, so it is not injective. But for surjective, it deals with the codomain. Everybody here should be paired with someone. So if I'm to put 8 in our codomain, you realize that it ceases to become what? Surjective. Because there is an element in the codomain that is not mapped to an element in the domain. So this is what we mean by what? Surjective. But if I'm to move 8, then you'd see that it now becomes surjective, because all the elements here are mapped to at least one element over here. Then we talk of bijective. When we say a function is bijective, then it is one-to-one and onto. So the onto is simply what? Surjective. It simply means it is injective and then what? Surjective. Or in other words, it is one-to-one and onto. So both injective and surjective. Perfect pairing of domain and codomain. Now, so for surjective, let's take an example. We are going to take the function f of x is equal to 1 over x, where x is not equal to 0. So for this function here, if I'm to substitute x to be -3, it is going to give us a negative what? 0.33. If I'm to substitute x to be -2, I'm going to get a negative 0.5. If I'm to substitute x to be -1, we get a -1. X cannot be 0 because it makes this undefined. Now let's go to x equals 1. So 1 maps to 1. 2 is going to map to what? 2 is going to map to 0.5. 3 is going to map to 0.33. Now we are seeing this type is actually bijective. Why is it bijective? You would observe that it is injective. It is injective in that every element here is mapped to just one, and they all have unique path. There is no two elements here that are all mapping to one element. No. Secondly, that is after proving that it's injective. Secondly, realize that all the elements in our codomain here have been mapped. There is no element in the codomain that has not been mapped. If we were to bring an element in here, it ceases to be what? Bijective. Because even though it is injective, it is not surjective. You get it? So it should satisfy both. Hence, if I'm to move my 8 from here, it now says it is what? Bijective. So that is it for these 3 types of functions we'll be looking at. So with all these done, we now want to look at how we can test whether a function is injective or surjective. And then we solve some questions. So there are basically 2 methods. If you want to test if a function is injective, all you need to do is to assume that f of x is equal to f of a. If you make that assumption, then you can now solve and prove that a is equal to b. If you're able to prove that a is equal to b, then your function is what? Injective. Another example is just find any 2 different inputs that give the same output. If you are able to do that, you have proved that it is not injective. So the 2 methods are force this and prove it to be true. If it is false, it is not injective. If it is, that is to say, if a equals b, then it is injective. But then, if you're able to find counter examples, that is 2 elements that give us the same answer, then you should know that it is not injective. This is how you can work them algebraically. But then there's a cheat you can use as well. That is if you are willing to graph out your function. So with this one that has to do with graph, then you first of all need to graph out your what? Your function. And we call it the horizontal line test. So for the horizontal line test, you simply draw a horizontal line across the graph. If the horizontal line is able to touch more than 1 point, then it is not injective. But if it touches just one, then it is what? Injective. So I'm going to take this horizontal line I have over here. So as I have over here, this is my horizontal line, you see? And as I take it up and then down, it just starts a line at just 1 point at each point in time. You see, at just 1 point. But let's take the second one, that is x squared, and then see what happens. So for x squared, this is the graph of x squared, right? Now if I'm to put my horizontal line on it, what do you see? You see it touches 2 points. You see that? So there are 2 points that our horizontal line will touch. If you are able to graph out your function and this is your realization, then you can conclude that it is not injective. You see? So here are the two methods. Now when it comes to surjectivity, we know a function is said to be surjective if what? The range is equal to the codomain. That is, there is no element in the codomain that is not mapped to by the element in the domain. So to test, all we need to do is to take any y in the codomain at all. You see, then you set your function to be y, and then solve for what? The x. This one would come more to life if we actually solve questions, which is what we are about to do. So with all these, let's now solve some questions to enhance our understanding. As usual, we'll be solving 5 questions, and I would advise that you take your pens, your books, and then try as much as possible to solve before unpausing the video to check the solution. Our first question we have here says, is this function, the function is f of x equals 4x minus 7, is it injective? We should prove it algebraically. We'll do that and then I'll plot it out so that we confirm our answer as well. Now we have said that for surjective, then we have an assumption to make. So the first thing we need to do is to assume that what? F of A is equal to f of what? B. So working this out, we have f of A. F of A simply means you are going to substitute the x here for A. So that we have 4, instead of x we have A, then minus 7 is equal to f of B. So instead of the x as well, we are going to put B over there. So we have 4, then B minus 7. All we need to do now is to prove that A is equal to B. So we should add 7 to both sides. You see, if you are able to add 7 to both sides, it eliminates the negative 7. So I'll be left with a 4a equals 4b. So if 4a is equal to 4b, then all we need to do is to divide both sides by 4. We divide both sides by 4, we have a being equal to what? B. And if a is equal to b, then it simply means what? F of a is really equal to f of b, which implies what? A is equal to b, and then the function f of x is injective. As simple as that. So this is how we prove that what a function is injective. First, assume this to be true. Be able to assume this to be true, then you prove that a is equal to b. because that is the only way you can also prove that f of a is equal to f of b. And if that is the case, then our function is injective. To try this out, let's get the graph and then see. So this here is the graph of 4x minus 7. You see, and using our horizontal line test, if I'm to bring this horizontal line down, it cuts this blue line just at one point. There are no 2 points that share this. So with that, we can simply say it is injective. You see. Let's look at our second question. It says we are to show that g of x, which is equal to x squared plus 3, is not injective on R. As I said earlier on, there are two ways we can do this. You can either look for a number, two numbers that will give us the same answer, or we can use algebra to do that. Now, for it to be injective, then we have to assume. So we have to assume that what j of a is going to be equal to j of b. If that is the case, then it simply implies that our g of a, that is substituting x for a, is going to be a squared plus 3 is equal to our g of b is going to be what? B squared plus 3. So with this, just as we did our previous one, the 3's cancel out. So we have minus 3 minus 3, which will be left with an a squared equals b squared. If you want our a, then what we need to do is to find the square root of both sides. So the square root of a to the square root of b, this one takes out this. You have our a being equal to, for b squared, we have what? B. Now take note, anytime we find square root of numbers, it gives us a positive and a negative. You see, and you know this as well can give us a positive and a negative. So it simply means that our a is equal to plus or minus b. And that is to tell you that there is an a value that gives us two other values. So this simply means a is equal to negative b and a is also equal to b. But that is not the condition for it to be injective. Hence, our function is not injective. Because for it to be injective, this is the only one we need. But this has come to join, and that makes it not injective on R. Now, if you actually wanted to use a counter example to solve this, then you can simply say that let's try. So this is just a try and error approach. So let's try, let's say 2 and then negative 2. So with that, we have our j of 2, which is going to give us a 2 squared then plus 3. 2 squared gives us a 4. So 4 plus 3 then gives us a 7. On the other hand, a j of negative 2 also gives us a negative 2 squared plus 3. The negative 2 squared gives us a 4. So we have a 4 plus 3, which also gives us a 7. This is a counter example to tell us that the function is a many to 1 because there are two elements here being mapped to 1. Hence, it is not an injective function. So our conclusion. So we can end it all by saying, therefore, j is not injective because there is a counter example here that proves that it is what? A many to 1. Now that we've done it algebraically, let's see if we can actually look at the graph and determine if it is injective or not. So this is the graph of the function g of x equals x squared plus 3. So with what we have here, if I'm to put my horizontal lines on it, what do you see? Is it that it touches at 2 points? But then we said for it to be injective, then all we need is 1 point. This is touching at 2 points. Hence, it is not injective. So that is all for the graphical method. Let's look at our next question. Our third question here says, is this function f of x equals 3x minus 5, where f is defined on this domain, R maps to R. Is it subjective? We should prove it. Now we know what it means for it to be subjective. At least our codomain should be equal to our range. You see? So what we said is we should take any value of y in our codomain R, right? So let's say take any y at all as an element of R. And this is to say that f of x then is equal to y. Now if f of x is equal to y, then it simply implies that the 3x minus 5 is equal to what? Y. Then what you do here is you make this x the subject. So making x the subject, we have x being equal to 5 moves to the other side to give us a y plus 5. You see, not forgetting our 3. Then what we do now is we divide both sides by 3. You see, so I'm going to divide this by 3 and also divide this by 3. With that, this 3 cancels out to this 3, and we'll be left with our x. So x is equal to y plus 5 over 3. Now with this, you ask yourself, is there any value of y here that makes this function undefined? Is there any value of y? No. Y is defined everywhere. So every y in the codomain is achieved. Since we can't prove that this is undefined, then it simply means it is surjective. That is how we do it. So first of all, equate the function to y. If you're able to equate the function to y, now make x the subject. If you're able to make x the subject, y appears at the right hand side. Then look for the value of y that makes whatever you have here not to exist. If you're able to find one, then it simply means your function is not surjective. So with this, we can conclude by saying, therefore, our function f is surjective. Now, I would want you to let me know in the comment section if it is bijective. We said it is bijective if it is both injective and surjective. This one here, you can easily prove whether or not it is injective. If you're able to prove that it is injective, and then over here, if prove that it is surjective, then it's bijective. But if it is not, then it is not bijective. Now let's look at the graph that represents this so that we have a visual of it as well. This is the arrow diagram representing 3x minus 5. And as you see, all the elements in the codomain is actually mapped to what? An element in the what? Domain. Hence, the codomain is equal to the range. Now, not only that, but all the elements here are also mapping to 1. So with the diagram, we know it is injective and then surjective, hence bijective. Okay. Our last but one question here says that the function that maps from real numbers to real numbers, and the function is f of x equals f of x equals x squared. The first one is whether or not the function is injective. Secondly, we have to determine whether or not the function is surjective. and then we should classify it. So let's start with the injective. We know that for injective, there are two ways we can solve it. It's either you find a counter example or you prove that f of A is equal to f of B. So I'll do both. That is, f of A should be equal to f of B. F of A here simply means my A squared. So A squared is equal to what? B squared. So B squared. And we were able to do this in our previous one. It means A is equal to a plus or minus B. That is to say, A has two values. And we know if it has two values, then it is not injective. If you don't want to use this, you can have also found a counter example. Two can work here. So we say f of 2 is going to give us what? 2 squared, which is a 4. And f of negative 2 is also going to give us what? Negative 2 squared, which is also a 4. With this, we are realizing that f of 2 is equal to f of negative 2. But 2 is not equal to what? Negative 2. Meanwhile, for injective, we said if f of A is equal to f of B, then A should be equal to B. But that is not the case here, and that is also not the case over here. It simply means the function is not injective. Now, to check for the surjective, we also know that when it comes to surjective, we have our function f of x, and we should always let it be what? Equal to y. Now, if f of x is equal to y, then it simply means y is equal to x squared. And we said after equating your y to your function, make x the subject. So making our x the subject, that is from x squared equals y, we find the square root of both sides. Finding the square root, we have what? X being equal to the square root of y. Now, is there any element of y that makes this undefined? Yes, there is. So if you take y to be a negative number, so let's even say just a negative 1, x ceases to exist. You see, so it means that among the real numbers we are talking about, y cannot be negative. You see, so if this here real numbers are our codomain, not all the elements in the set of real numbers are actually in the range. So that alone should put you off. And that alone should tell you that your function here is not surjective. Why? Because we have elements in the range. So we have elements in our codomain, and our codomain is made up of all real numbers. Real numbers, we have integers, we have whole numbers, we have counting numbers. The integers are made up of positive and negative numbers. But y is not satisfying the negative numbers. Hence, it is not surjective. Simply means there are elements in our codomain that are not going to be in our range. So our conclusion is going to be simple. That is to say, our f of x, that is x squared, which is defined on our set of real numbers to real numbers, is neither injective nor surjective. Now you realize that to test for its surjective, you realize that to test for it being injective, if you have to take our graph, this is the graph. First of all, there are 2 points on my horizontal line. So that alone simply means it is not injective. Then for surjective, look at the y. They have positive and then negative numbers. It only subjects itself to the positive. It has no say here in the negative domain. It is being partial to the positive. So that will be it for our visualization. Now let's consider our last question for this session. So our last question here, it is actually very, very simple. It says our function f is defined on what? A to b, where A is this set and then B is also this set. F is defined by f of x equals 2x. And the question is we have to list all the ordered pairs. Secondly is f injective, C says is f surjective, and then D says is f bijective. So our solution, let's start with the first one. So we want all the ordered pairs. We know our function is giving us what? F of x equals 2x. So it simply means our f of 1 is then going to be what? 2 times 1. We are taking the x's from our domain. This is our domain, and this becomes our codomain. So 2 times 1 is going to give me what? A 2. Then we come to f of 2. So for f of 2, I have 2 times 2. And 2 times 2 also gives me a 4. Then for the last one, we have f of 3. For f of 3, we have 2 also times 3. 2 times 3 gives us a 6. So for our ordered pairs, it's going to be what? 1, 2, 2, 4, then 3, 6. Now, if you were to get the arrow diagram for this is how it's going to be. So as you can see over here, this is just it. And then this is how its graph is also going to be. Very simple. Now the question says we have to determine if it is injective. We've done how to prove that it is injective already. Okay, so each and every element here should map to 1. And as you can see, it is being mapped to 1. So you can prove it using the algebraic method. Hence, it is injective. Then for surjective, each element in the codomain should be what? Mapped to 1 element, so that our element in the codomain becomes the range. And as you can see, that is also happening over here. All the elements here are mapped to 1. And since it is both injective and then surjective, then it is bijective. And that is all. We'll be ending this lesson here. As usual, I'll leave you with some exercises so you try on your own. So here you are with 5 questions based on what we've done in this lesson for you to test your understanding on. They are very, very simple. And if there's any issue of concern, you can always let me know in the comment section. This is How Beyond Numbers, where we learn maths the easy way. If this is your first time on this channel and you so do wish, you can choose to subscribe so that anytime I release a video, you'll be notified as well. See you in our next lesson, and bye for now. Do stay safe.